Okay, environmental chemistry, outcome number 3. So we're looking at the dangers in the dose. Toxicity is the ability of a chemical to cause harm to an organism. So a chemical has acute toxicity when serious symptoms occur after one exposure, like cyanide. There's nothing cute about acute toxicity. One exposure, you're sick or dead. And acute means sharp, so acute toxicity means sharp toxicity. Now, chronic toxicity is diagnosed when symptoms appear only after a chemical accumulates up to a specific level after many exposures. Uh, Kind of like DDT. DDT had chronic toxicity, right? It had to build up. DDT had chronic toxicity like in the dolphins, acute toxicity in the insects, right? Because one exposure, the insects are dead. But in the other organisms higher up the food web, it took many exposures before they would get sick or dead. Okay? Like lead poisoning is another one. Any lead you come across in your life builds up. Eventually, if the concentration gets high enough, you get chronic toxicity. Uh, Fentanyl, acute toxicity, right? One exposure, sick or ill. You could argue that cigarettes have chronic toxicity. It takes many exposures before you're sick or dead. Now, the amount of exposure is important, but the effects will vary because everyone has different body masses, metabolism, genetics, lifestyle. We're all different, which is why it's hard to establish a safe what toxicity is. And on top of that, most of the testing is actually done on rats. And so rats are very similar to us, but not exactly like us. So you always have to take the published values with a grain of salt. So here in this chart, the question would be, out of these mineral pollutants, which one is the most dangerous? Well, the most dangerous one would be cadmium. You're only allowed 0.017 parts per billion in your drinking water before it becomes toxic. What's the least dangerous in this chart? Barium. You're allowed to have 1,000 parts per billion in your drinking water, so this is less dangerous than this one. And then how do we measure this toxicity? Well, one way of measuring it is lethal dose 50 or LD50. Lethal dose 50 is the amount of chemical it takes to kill half the population to which it's applied. Okay, so like here in this chart, we can see all these numbers, right? For toxin, botulinum toxin A, with the source is the bacteria, Clostridium botulinum, at 0.000000003 parts per million in your bloodstream, that would kill you. Like, how do we figure out LD50? It would be you take all 50 mice and give them, I don't know, what's toxic? Monster energy drink. Give them Monster energy drink until of the 50, 20 of them die. Okay, and that is what LD50 is, the amount of chemical it takes to kill half. So this is the most toxic one, right? Because the smallest concentration will kill half of people. Dieldrin is the least toxic of this because it takes 80 parts per million in your bloodstream before half the people would die. Okay, you'll notice that the toxins made by bacteria are way more lethal than any human-made poisons. And LD50 is a very useful guide in letting us know how to handle certain chemicals. Now, government agencies and legislative bodies are often pressured to try and relax their strict testing before a new drug or substance is approved. We see this right now with all the vaccines that were out there for COVID-19. They've been trying to push the testing to be faster and faster. It still needs to be done so that it's safe. Otherwise, there could be drawbacks. I don't know if you ever saw the movie Legend, where they found a cure to cancer and then it turned everybody into these weird zombie things. Well, you could argue they didn't do enough testing. Really good reasons to have all this waiting period in place. Not all individuals or species react the same way to a particular chemical. The toxicity of a chemical depends on how much enters the body and how much contact is made with the chemical. And so is it eaten, or did they breathe it in, or was it exposure to skin makes a difference? We can't rely completely on published toxicity values because few actual measurements have been made. We haven't had enough people die from accidental exposure to actually get a reliable toxic concentration that would apply to everybody. And also, most testing is done on rats and mice who aren't exactly like humans. So we always have to be careful when we look at the results. Now, despite the best efforts of scientists, sometimes a drug will be approved with tragic effects. Like the drug thalidomide, a good example. It was a sleeping pill, prescription sleeping pill. Pregnant women, when they get into certain parts of their trimester, have problems sleeping, and so they were actually prescribing these to people who were pregnant and not pregnant. And its use by pregnant women in the 1950s resulted in thousands of babies being born without limbs. And so I think I don't have the picture there. Okay, now it turns out rats could tolerate 4,000 parts per million. Pregnant women, 0.5 part per million started having effects. Okay, and so there's a case where nobody actually thought to test it on pregnant women to see, or pregnant rats to see if it would have an effect. Yeah, let's see. There we go. So, with all the publicity about toxicity of chemicals and their abuse, we tend to overlook that most toxins are natural. In fact, natural toxins are way more dangerous than human-made ones. Now, we take risks in every type of daily activity, right? Walking into the school from the car, I could risk turning my ankle if I step off the curb the wrong way. Does that mean from now on I'm going to walk around? I'm not going to walk. I'm just going to get a wheelchair? No. The risk of spraining my ankle doesn't prevent me from going for a walk. We are more concerned with what's an acceptable risk, right? Even coffee. There are chemicals like caffeine that has LD50 of 130. Does that mean we shouldn't drink coffee? Well, it would take 70 cups of coffee at once to get a lethal dose. Now, your stomach can't even hold that much liquid, so it's not of a concern. And this number may not be as accurate because the testing was done on mice. Now, I did look it up. The maximum amount of caffeine someone my size should have in a day is 190 milligrams. Okay, and so I looked it up. I'm not getting anywhere close to that. We should worry about this, but because there is caffeine pills, and you could take enough caffeine pills to overdose, because each caffeine pill is worth about 5 cups, and they sell them in packs. 7 cups, and they sell them in packs of 12. So 7 times 12 is 84. You could hit LD50 with that, in which case you'd have a 50% chance of dying if you took them all at once. Now, the evaluation of risk and benefits of any chemical forms the basis of how chemical use is regulated. Like someone says, just ban all the use of chemicals. Well, there is a pesticide that we spray on strawberries to get rid of the mold. It's a fungicide. Well, and if we don't spray with it and you eat the mold can cause you to develop cancer. So the question is, which one is better or worse? And then you have to analyze the risks and make a decision. And that is the end of topic 5. Oh, no, that was the end of topic 4. So topic 5, getting away from it all. We're still in outcome 3, part 1. All living things explore their environments to the best of their ability. Materials and energy are taken from the environment, and waste products are just posited. Waste from one organism becomes a resource for another. The environment overall remains balanced over time, unless, of course, waste is produced faster than it can be removed. We have this perfect cycle that's been going on, right? We urinate, we poop, we give off carbon dioxide. That goes to the plant. It takes all that, it grows, it makes sugar. We eat the plant, and that cycle's been going on for, pretty much for all of life. Watch out, humans put this out of balance. The population used to be small enough that the environment could actually handle our waste. It can't handle waste from 7 billion people today. I think this is the population counter. World population count. Let's see if it'll allow us to see this. 7.885 billion is the population today, and increasing. Okay, and so, whoa. Okay, we can't handle waste from that many people. And so here is a factory, and there's a farm, and there's a ranch, and there's a city, and there's the mountains. The question is, what kind of pollutants are coming from where? Well, the pollutants could be entering the river from the factory waste, the agricultural runoff, right? It could have fertilizer, pesticide, and it could have animal waste in it too. The sewage from the city, the storm drains from the city, acid precipitation at the clouds. These all are pollutants that could places where pollutants can enter the river. What kind of pollutants would they be? Well, from the factory, it's organics and heavy metals and hot water and carbon dioxide and the exhaust. And from the city, we have sewage and phosphates and fertilizers and pesticides and organics, car exhaust, animal waste as well, because we all have pets and that sort of thing. From agriculture, pesticides, fertilizer, animal waste as well. Those are all pollutants that can cause problems. Now, in environmental monitoring, there's two kinds of waste. There is non-persistent waste. Non-persistent means it does not persist. It doesn't stick around. And so fertilizer, sewage, apple core, these are wastes that can be broken down into simple non-polluting compounds by naturally occurring chemical reactions or biological reactions. They tend to be the biodegradables. And fertilizer and sewage and apple cores, those are non-persistent wastes. And then we have persistent waste. Persistent waste, they persist. They accumulate in the environment. They tend to break down very slowly. Some of them don't even break down. They tend to be non-biodegradable. So what are some things that are persistent, that persist? Pesticides, right? DDT, 150 years. Petroleum products, dirty oil, heavy metal waste, all these persist. And they're both a concern if they become concentrated enough to harm living things. Now, how do we figure out if pollutants are present? The easiest way is to go and test the water source nearby. Basically, all pollutants eventually end up in water. Okay. Now, if we know the test for pollutants, we can determine how much of that there is. You could test like in a lake or a stream. You could test it in the snow or the rain. You could test it in the groundwater, and that's where you'll find pollutants if they are present, because they always flow that way. And it says this was still outcome number 2. Point source versus non-point source. Determine the presence of a pollutant is first step. The next step is tracking that concentration to find the source of the pollutants. 2 sources of pollutants there's point source pollutants, okay, and that's where the pollution, basically enters from one specific. This was in topic 2. We've already covered this. And there's non-point source pollutants. I'm not sure why that's there. And let's stop there. This is all, I'm pretty sure, outcome number 3.